The peacock mantis shrimp is well known as one of the fastest animals to exist in the animal kingdom, bearing a stunning punching speed that matches that of a .22 caliber bullet. As such, for my final project, I have decided to analyze the punching speed and force of a mantis shrimp attacking a fiddler crab. Indeed, it is easy to discern that the mantis shrimp strike is extremely fast. Though, the question is, how fast?
So first things first, it's important to know that the length of the shrimp claw, so this part around here, is around 2.65 centimeters, which will act as our radius. And I use this as a reference in order to figure out the general delta XX, which is this distance, and delta XY, which is this distance, that the shrimp claw travels in order to get towards the crab claw, which I set to being around 0.5 centimeters and 1.5 centimeters respectively. Furthermore, the clip I used was already slowed down by 0.5 times its actual speed, but I furthermore slowed it down by 0.1 times the speed to make plotting the points easier. So the actual time it takes, based on what I gathered using the video analysis app, was 0.05 seconds prior to the collision and 0.35 seconds post-collision. And I was able to furthermore figure out by using Google that the mass of the crab is around 0.003 kilograms and the mass of the shrimp is around 0.039 kilograms. And I furthermore assumed that the shrimp claw travels around a sixth of a total circumference. So like around this much would be like a sixth. And that the collision is elastic since the crab's claw gets completely blown off by the collision, as shown in this graphic I made, sort of representing the relationship I'm analyzing. In order to figure out the velocity and the acceleration of the mantis shrimp claw as it before the collision and after the collision, I used the video analysis app using the original video of the mantis shrimp attacking the fiddler crab, in order to create a graph both pre-collision and post-collision for what the velocities may be. And so from here, using these graphs, I was able to discern that the vertical and horizontal velocities, both pre and post-collision, for the mantis shrimp claw, which are these following equations I've displayed here. And using those, I was able to discern the average velocity for pre-collision and post-collision, using those vertical and horizontal velocities. And I plugged them in order to find the acceleration, both before the collision and after the collision, which are the following values. And finally, using Pythagorean theorem and converting the units for the vertical and horizontal displacement into meters, I was able to discern the delta X that the shrimp overall travels during its trip across, to hit the crab. The linear speed isn't the only thing we can discern though, because using the linear speed and the value for the radius that we had displayed or that I had used earlier in my givens, I was able to furthermore determine that the angular acceleration, using the acceleration I'd gotten earlier for the initial acceleration, is around this value, and the final angular acceleration is around this value. And I was then able to use these using the rotational kinematics equations to find the initial angular velocity and the final angular velocity, which are these following values. And I was furthermore able to then figure out that the inertia of the shrimp was around 0.02 times the mass of the shrimp, which is the percentage that the mantis shrimp claw takes of the overall mass, times r squared is around this value, and that would be its inertia. And so using that value and the discovered angular velocity values, I was furthermore able to discern the angular momentum for all of these. For the forces of momentum, I set the masses used in the equations as 0.02 times the mass of the shrimp and 0.05 times the mass of the crab, because those are the relative percentages of the body weight that the claws take up for each of the for both the crab and the mantis shrimp. And so I utilized those values in my momentum and force equations. Now, for my momentum equations, I wanted to use the conservation of momentum in order to discern if the force of friction was negligible in the equation for forces. And so I set that as 0.02 ms times the initial speed of the mantis shrimp as being equal to the mantis shrimp's final momentum added with the momentum of the crab after the collision. And so in order to discern PC, which is the momentum of the crab, I utilized the crab's impulse, which I was able to discern through this vernier video analysis graph, which, as you can see, it goes from nearly not moving at all to just immediately jumping up to this point. And I put this into Desmos in order to discern the exact values for the velocity that these two display. And so then I use that in order to discern the impulse, and therein find the find PC, which I found was around 2.0085 times 10 to the negative 5 kilogram meters per second. And I furthermore found this by, finding the velocity of the crab after the collision, which I just basically did by finding the final velocity subtracted by its initial velocity, and took the vertical and horizontal components that I found in the Vernier video analysis app. And so using that and plugging those values in, I was able to discern that this side of the initial momentum is much greater than the final momentum, and therein that means that the force of friction isn't negligible because the momentum has been reduced, and that means something outside of the system, likely friction, impacted the momentum. And now finally the forces. So I set up this diagram for the so this is wrong. It's supposed to say the shrimp claw, because this is the forces applied onto the shrimp claw as it moves to strike the crab claw. And so this is the force applied by the mantis shrimp through the claw. This is the force of friction that it experiences from the water as it moves, and this is the force of gravity applied onto the shrimp. And so first things first, I was able to discern that the force of gravity for the mantis shrimp, and I used the mass of the entire shrimp for this one, is equal to 0.39 newtons. Now, I used the mass of the entire shrimp because I assumed that the same amount of gravity would be applied to all parts of its body. And furthermore, I assumed that the net vertical forces were equal to 0, since most of the force that the mantis shrimp appears to move in a horizontal direction rather than a vertical direction, purely just from visual observation. And also for simplicity's sake. And so I set the Fg plus Fay as equal to 0, the vertical component of the applied force. And so from there, I was able to discern that the vertical component of the applied force is also 0.39 newtons, just like the force of gravity. And so then, using that value, I was able to use trigonometric equations and set the horizontal component of the applied force as equal to the vertical component of the applied force multiplied by tangent of theta. And I assume that theta is around pi divided by 3 radians, since it moves around a sixth of the total circumference. And so plugging that in and plugging in the value for Fay, I would figure out that Fax would be around 0.675 newtons. And then furthermore, I didn't write the 5 fully here, but I then used Pythagorean theorem in order to discern what the actual applied force is, which would be equal to 0.6084 newtons, as specified here. Now on to the really fun part, which is actually finding the frictional force. Now, we can't use the normal equation for the force of friction we learned this year because it's invalid since the force of friction occurs in a fluid, meaning we would have to use drag or fluid friction in order to find it. And since I don't possess nearly enough knowledge in order to actually use fluid friction, and we didn't learn it this year, I instead chose to just figure it out by using the net force and setting it equal to ma. And so I set the force of friction added with the force applied with the force of gravity is equal to the mass of the shrimp times its initial acceleration, since that's the point we're measuring the forces from. And so I figured out that the force of friction added with the values is equal to this. And so then I was able to discern the force of friction from there as being around 0.172 newtons. And that concludes this experiment.